So to get started, this is a tutorial on basically approximate Bayesian methods. So we're going to start with some recapping some theory, talk about variational inference, take that from the basics of linear regression stuff we would have seen before probably, all that to generative adversarial networks. And in the last section, we're going to have a quick overview of some really recent work, kind of uniting the two schools of implicit and explicit generative models. It's actually being published in ICLR and presented tomorrow, so we're beating them by a day on that research. So just a quick recap. Who am I? I'm a senior ML researcher at Longshot Systems. We do high throughput, low latency trading software for sports betting markets. We have some really interesting problem areas. At the moment, we're actually hiring for a Python developer explicitly, but we're happy to meet with people from a range of skill sets who are interested in maybe finding out more about what we do. Got 3 guys as well with me down the front here, so if you're interested to talk more about that, come find us afterwards. Okay, so as always with these presentations, just to head off any questions about why PyTorch or TensorFlow, I'm opening with that. I've used both. I used to be a TensorFlow when it was basically just TensorFlow. They both have pros and cons. I mean, if you write Python a lot, I think PyTorch is way more similar to what you do. It's very easy to just switch in and out from NumPy into PyTorch pretty quickly. Downside, it's pretty new. It's very, very bleeding edge at the moment. Basically, half the functionality this talk uses is in version 0.4 it was introduced. That landed 2 days ago. So if you're prepared and installed more than 2 days ago, you have to upgrade. So that's obviously a downside. It's very alpha at the moment, but it's doing really great stuff. Okay, just a point of notation, because we see some formulas and stuff. I think it's generally agreed upon standard, but just to recap, small case, non-bold means like a one-dimensional data point. Bolded means multidimensional. That can include 1D, because that's in a multidimensional space as well. And capitalized normally is a matrix. And then the standard Y is generally a target and W a weight. Okay, so if you want to follow along, this is my GitHub page with all the slides and the notebooks on it. I'm not going to run any code here today just because lots of these models take a while and well, I've already run them, so we can see the output. I'm not sure it's instructive just to watch something train particularly, so feel free in your own time to go through them. So some prerequisites. I kind of expect you've seen probability before, and basic Bayesian terminology, and some reasonably broad ML knowledge. If you don't know what regression is, it's probably going to be a hard hour and a half for you. So what we're going to do today, like I said, recap some key ideas, kind of try and lead a fairly consistent path through variational inference, probabilistic discriminators, VAEs and GANs. Like I said, there's lots to cover. When you're putting together a talk like this, it kind of, you either have to put a lot of stuff in there and hope people go away and do a bit more, or we have to concentrate on one thing and basically cover nothing for it. So there's probably going to be stuff that's going to go over your heads, but there's lots of resources at the end of the slides as well, so you can come back and see other people talk about them and get a different perspective if you want. Okay, so motivation. This talk is about doing approximate Bayesian inference. So the standard one that we probably all see in probability textbooks everywhere is a coin toss. So if I toss a coin 20 times, I get 5 heads and 15 tails. What does that mean about the distribution of the coin? In sort of a Bayesian framework, I'd be saying I'm looking for a posterior distribution of the coin's bias, so like the probability that it's heads versus tails. And this is obviously a very standard problem, Bayes theorem. I'm sure you've all solved it in probability class or whatever. Most real-world problems they follow the same idea, but they're nowhere near as simple. And so we need to use approximations because the maths breaks down very, very quickly. Variational inference is a subset of approximate Bayesian inference. Basically, if it uses optimization to solve the problem, it's generally called variational inference. Things like Markov chain Monte Carlo also fall under approximate Bayesian inference, but not necessarily variational inference. Okay. So what kind of problems is it useful for? Well, I mean, as it says on the tin, anytime you're looking to apply probabilistic reasoning, so that means if you want to get uncertainty estimates for things like classifiers and neural nets, or you want a true predicted distribution. So we'll see some examples in a minute about what that really means. But if we use a naive approach, like we train a neural network and we just throw in our data, our out-of-sample data, we might get a probability, but it's not really predictive because we don't really get a measure of how much that input point represents what we trained on and how similar those things are. And also, there's been a lot of success recently in using these methods to kind of shine a new light on things that we know that work in practice. So things like dropout is probably one of the most famous ones that we can reinterpret in a variational inference type framework, and it allows us to apply theory and probabilistic reasoning to stuff that we know works empirically and we discovered empirically. Okay, so the cornerstone, I hope you've all seen this before. Okay, I'm probably not going to dwell on that anymore. And this is, again, a textual description of Bayes' theorem. You know, normally you have parameters, theta normally, and a likelihood is a function which gives you the probability of your outputs or your y's or whatever, given your thetas. Your prior is your prior belief, so this can be anything from uniform up to some very specific belief. And the posterior is how I update my distribution of the parameters now that I've seen data. And so these are the terms in Bayes' theorem, as I'm sure you've all seen before. Okay, so we have to cover a little bit of information theory. Hopefully you've all seen this as well. So a divergence measure is how we essentially measure difference, is probably the best term to put it, between probability distributions. So you can think of it at a high level as like a distance metric, but formally to be a distance metric, it has to obey a set of relations, basically, which are given here. And we can relax some of these, so like symmetricity doesn't necessarily need to hold for a divergence measure, like KL divergence is not symmetric, but it still gives us a quantifiable way to measure between distributions. So the KL divergence is probably the most popular one. Hopefully most of you have seen this before. It's not symmetric, so you can see it's the expectation of, under the distribution of Q, of the log ratio of Q and P. So if we were to permute Q and P there, P would be the expectation term, so that's obviously not in general the same if you do PQ and QP. And this difference, the non-symmetric nature of it, induces different preferences when we learn. So if we have a look at our first demonstration. Okay, so at the top here we have the, I hope you can see that. We have the definition of the tail divergence again, and this is the reverse form, so this is what I was talking about before. Now, because we have a ratio in the log term, if we have, depending which formulation we have, if the denominator is small, that causes the whole term to blow up, whereas if the numerator is small, then it causes the whole term to be small. So depending which way you have the ratio, induces different preferences, basically. So what I've done here is used SciPy has a KL divergence function, so I've just used that and defined a probability distribution which is a mixture of two Gaussians. Very straightforward. So if we were to imagine this was what we're trying to learn, and what we're going to fit a normal distribution to this, just a single one. So if we, so Q is our approximate distribution we're trying to use, and P would be the mixture. So if we're trying to optimize Q using QP, we can see that this exhibits what we call mode-seeking behavior. So it sees the best approximation as matching one of the modes of the two. Whereas if we were to use the reverse formulation, we can see it actually prefers mass covering. So, and this is because it's, again, because of the ratio, it's penalized for there being mass on the real distribution and no mass on the approximate distribution. So which formulation you use actually matters quite a lot because it depends what you're looking to do, because For example, the first distribution, if you're looking to get really good samples from across the whole distribution, this is a terrible approximation because you just missed out like half the distribution. But if you're kind of looking for more, I want to understand the true variance and things like that, this is a much better thing to do. But equally, any samples you draw from this are not going to be as representative of either mode. So you have to think about these things when you're designing your system. Okay. So with the preamble done, we can move on to the meat of the talk, I guess. So why the posterior? We kind of saw an example earlier. But, the reason we care about the posterior is because it allows us to compute other good stuff, really. So if we want a true predictive distribution in the Bayesian sense, then this is the formula. So it's essentially the expectation of the out-of-sample likelihood with the posterior. So this is useful for out-of-sample predictions and uncertainty estimates. And also, maybe you want to do what's called Bayesian high-parameter selection. So you need what's called the model evidence. And we can compute this using the posterior as well. Normally, we assume the joint is tractable, because this is just multiplying two terms together, whereas the evidence is not because, or the posterior is not because it involves an integral term, as we'll see in a minute. So there's two main reasons why we would use these methods. So why would we ever need to approximate? Well, simply computational requirements. Because if we look at Bayes' theorem, we can see that the denominator of Bayes' theorem has an integral in it. And this is fine for some distributions, like we know certain class of distributions, like two normals make a normal and everything like that, which is normally termed conjugacy. But for most real-world examples are probably not conjugate. We just do that to make it easy. And for any two distributions, the chances are if I just made a joint distribution, tried to integrate it, I wouldn't have anything that was anything we knew as a distribution. So if there's no easy analytical answer, you basically, if you want to compute this directly, you'd have to do numerical integration. And this is really not scalable because you hit the cursor dimensionality very, very fast. So just as an example, if sigma is a sigmoid distribution, there's no closed form solution to this. It is just a thing, but we could compute it numerically, but there's no, I can't just say this is like a beta distribution. This is just what it is. And so the only way to actually get an answer to that would be to do it numerically, and we'd very quickly run out of computational resources. It would be extortionately expensive. Okay, so just to kind of start on our path, we're going to look at Bayesian linear regression. So I hope most of you have seen this before. If we have a prior distribution over our regression weights, which is just a standard normal with a diagonal covariance matrix, and a likelihood, which is a linear function in the mean, a diagonal covariance, we can derive, because we know that this combination of models is conjugate, we know that posterior is conjugate, simplifies our algebra a lot. I don't know if you've never done this before, it's a reasonably worthwhile exercise. You can see something like Bishop for the steps if you're interested. But basically, these two terms at the bottom here are the mean and variance of the posterior. So I've got that just implemented quickly in NumPy, so we can... Okay, so this is just a recap again of the model that I just showed on the slide. I've just used what's termed a basis function expansion. So these are our x's here, denoted by the phi's. And we know what our posterior looks like because we've got the answer already. We've done the maths. So it's nice and straightforward. If we generate some data, and we essentially are doing a basis function, which is a third-order polynomial down here. So we're fitting a third-order polynomial to this data. And so basically all this code is just implementing the formula that we saw above. It's not particularly interesting. But what we do get is we get the mean and covariance of the posterior, which we can use numpy.random to sample from. So when we do that, and we plot the different regression curves, basically, we can see that this is a reasonably good posterior, because when we sample from this distribution, most of them fit in the data quite well. And what we see is that the variability starts to increase as we go outside our data, so especially on the left-hand side. And this is kind of well-known. Extrapolating partial data doesn't lead to sensible things sometimes. So this is the kind of thing that posterior allows us to see. So we can use the predictive distribution now, which again relies on the same matter before of conjugacy. So this will give us, if we implement, this again, we can sample from this distribution, which is our predictive, which I've done here. Again, it's very straightforward, which is just implementing the formula we saw above. And what we get is a plot of confidences, for want of a better word, about the location for any x. So for any x, this is like a heat map of what the probability is of y being at that point. So it's very high around the data, which is good, and very low when it's not around the data. But the interesting thing we see is if we zoom in a little bit, we can see that as we move past our data, our model gets less confident to predict any point. So this is actually really useful, because if we're doing things where, like, we're landing an automatic aircraft, we want to be really confident that this isn't just like some overfitting artifact, and this is actually what we've seen before. So having a system where it starts telling us when, oh, your input, this is what I think the input is, but this is quite far from anything I've ever seen before. And this is what you get if you use a Bayesian approach, because even though it will still predict, the mean will still be the same with this distribution, we can see up here the probability is significantly reduced, so we start to get a signal that we may be extrapolating past the end of our data. Okay, so that works nice and easily, so it's all analytical. All I was doing there was just implementing some maths in NumPy. The reason that works is because of conjugacy. So we know a normal likelihood with a normal prior on the mean is still normal, and so we get, and everything's all nice. But we may not actually want to use this in reality. I mean, normally, so the likelihood being normal means the errors that we observe are normally distributed. Normally we justify this by saying, oh, well, it's probably lots of little small errors that all add up, and then I can just say it's a central limit theorem and not worry about it ever again. Depending on what you're doing, that may be not true. You might actually have one single source of error that's clearly not normally distributed. If you want to do that, so you wanted to have like a log normal distribution of your error, it wouldn't work. You'd need, because that's not an analytical solution anymore. And for example, the normal distribution also implies symmetricity, so that's maybe a strong assumption for some cases. So, like for example, house prices. If you're trying to regress like true house, to learn the true house price given the price I put on the market for, I'd probably be a safe bet to assume that that's not a symmetrical distribution. People are almost certainly going to put houses for more expensive than they're worth a lot more than they are for less expensive than they're worth. No one wants to sell for less than the house is worth. So if you actually cared about being precise about this model and the predictions you make, you wouldn't be, using a normal likelihood would probably be the wrong way to go. And also, if we have things like our likelihood is not just a linear function of our prior, and we want to use more complicated ways to determine the mean, then also our conjugacy disappears, because it only works because it's a linear function. So normally, the first place we ever see non-conjugate distributions to do inference when we're learning about machine learning would be the Laplace approximation. So if we're doing logistic regression and we want to do that in a Bayesian way, this is normally the first example. This is a historical approach. It's an analytical approach, which we have implemented here. So the model for Bayesian logistic regression, it's basically the same as linear regression, except the likelihood is wrapped with a sigmoid function. So because this is actually classification, our outputs are 0 or 1. So we can interpret this as being like a probability that y is class 1, for example. So this is because of the sigmoid, which is obviously a nonlinear function. then we no longer have a conjugate set of distributions. So the posterior here is not conjugate, so it's not normal. And so we have to rely on an approximation if we want to do this. So the standard way would be to use a Taylor series expansion. I won't spend too much time on this, I promise, but basically you do a Taylor series expansion of any log function in general is given here, and we say, okay, we're going to take the Taylor series expansion around the map point, so essentially the mode of the posterior. Because it's the mode, it's a maximum point, so its first derivative is 0, which allows me to get rid of the middle term in here. So this guy is 0, so all this whole term drops out here. And then we can essentially recognize all of this as being, I don't know, some number, because it's a derivative at a certain point, which we just call that A. And so this actually starts to look a lot now like the log PDF of the Gaussian. So that's essentially what they do, is they say, I'm going to take a Taylor series approximation of this posterior using the second derivative at the map as the covariance matrix, and then the map point as the mean. So this is what I've got implemented here. Hopefully you've all seen logistic regression implemented before. It's quite straightforward. So I've just used a torch linear layer here, which is just a weight matrix times your inputs. And then we have a loss function, which are binary cross entropy, standard classification, negative log likelihood, and a prime, mean, and variance, again, which is just defined as as a 0, 1 with a precision multiplier. I don't know if people are familiar with the torch kind of paradigm, but generally use forward to denote the forward pass of your network, for want of a better word. So this is just working out, So this just works out the linear function, because our loss function takes logits, and then we can apply sigmoid to this function as well to get the proper likelihood output, which is given here. So the way we do this analytically is we do map estimation. So we put a prior on the loss function, and we solve that, and then we just plug in this analytical term here as the covariance, which is what we've done here. So we've got negative log likelihood, which is just the exponent of a normal distribution. So if we take a really simple classification example from scikit-learn, so 2 classes, 4 blobs, we can pass this data into our logistic regression, and we'll just use Adam to optimize it. We minimize our loss, which is our likelihood and our prior, and we get a single weight value out. And from there, we can just, for example, visualize the classification surface that we learned. So it did a very good job. Most of the data points are correctly classified. It probably could do a little bit better, because these look like maybe they're on the wrong side. It's hard to tell sometimes because of the plot size. But this will be an influence of the prior as well, because it favors much more simple zero mean weight functions. And so if we now essentially just do that maths, again, a bit like we did in NumPy, and we work out what that second derivative is. It's a nice analytical form. It's not particularly pretty, but we can work it out quite straightforwardly. And this is the mean here, so this is just the weight I've learned from my logistic regression from the previous step. And so we can do exactly the same thing now. I can sample from this distribution, which is actually a torch multivariable Gaussian, and we can see that we sample all these different separation surfaces. And so, again, our posterior looks reasonably sensible. And we can do the same thing again. This is classification this time. So we can say, okay, so imagine I now want to classify the point 100.5. So this is obviously like really far away from any of the data we've seen before. And if we did a Bayesian prediction, we'd get an 80% probability. But this is because we're computing an average over all these decision surfaces. So because they're different, some of them will it will fall on one side and some will fall on the other. But if we just used the map point, so the most likely weights that we've determined, we'll see it will be super overconfident. It tells us 98.7% that this is on class 1, which is probably strong to be that confident on a point which is of an order of like 10 times further away than any point you've ever seen before. So this is why we do things like a Bayesian predictive distribution, because we get slightly more well-calibrated probability outputs, as opposed to just taking a single output and deciding that's the one. Okay, so that was great, but it has some shortcomings. We had to resort to actually doing the maths. We had a Taylor series expansion, and it's not kind of clear how that would work if we wanted to use some other distribution as an approximation. If we wanted to use a mixture of 3 Gaussians, that's going to get pretty messy. The Taylor series doesn't look like anything like that, so we're not really sure how we'd proceed from there. So what we can do is resort to a much more modern technique, which is a lot more general. And so this is called the elbow. It also appears in the EM algorithm. If anyone's ever seen that before, this is the same loss function, for want of a better word, in the EM algorithm. It tends to be derived slightly differently in variational inference literature, but to all intents and purposes, it's the same thing. So the first point is that you're looking to minimize, so I want an approximation Q, which minimizes the distance between, so the distance is in the KL divergence between my approximation and my true posterior here. And so we can go through the algebra. It's relatively straightforward, just chopping up the, so taking this is the definition of the KL divergence. We can chop that up using Bayes' theorem, do some rearranging, and it drops out that we can say that the log likelihood of our data y is greater than this term here, which we call the elbow. So the idea being that because this KL divergence is, so we can't compute this because we don't actually know the posterior, but we know it is positive because the KL divergence is never negative. So we can just drop this term, turn this into an inequality, and we have a bound. And so this helps us because we have an optimization problem now, because instead of having to compute this term directly or something, we can just maximize this term, and we know that if we maximize it fully, we're going to get inequality, and our approximation will be exact. So it allows us to transfer from probabilistic methods into optimization, and we have a lot more tools to help us out there. So we can do exactly the same thing we just did with the Laplace approximation, but we can use the elbow instead as a loss function. Yep.
What does elbow stand for?
Evidence lower bound. So it's a strange name, but okay. So we can use the elbow as our loss function now. So it's the same model as we saw before, so this is the form of the loss function. This is the form of the elbow, sort of chopped up. So we have basically, you can consider this to be like a simplification term or a regularization term. So it penalizes the difference between our approximation and our prior. So it acts to damp down complexity. And this is kind of, you can call it like a pseudo-likelihood term. So this is the term that is high when our reconstruction is good and when our approximation is good. And so we have an interplay between simple models and complex models. And hopefully this allows us to find a nice, happy medium. And so this is pretty much the same code as before, except now we have also 2 parameters which are a mean and a variance, or a covariance. So whereas before we essentially trained just our weights, so we can see that as training a distribution with just a fixed covariance that we know. Now, because we want the full distribution, we have to learn a covariance as well. So we have an extra parameter that we have to optimize for, basically. Everything else is exactly the same. So we've got our forward is basically the same. I haven't used linear here just for simplicity. So, and in the loss function now is an implementation of the elbow. So the expectation of the likelihood is just, again, it's a cross entropy. And for the KL divergence term, we've got because I'm using a Gaussian to approximate this, just to be consistent, we have an analytical solution, so I've just implemented that. We could also do it with Monte Carlo. It doesn't really make any difference, it's just a little bit easier for me this way. And so if we see, so this is a slightly different problem, but same idea. Now we have one subtlety in that if we want to learn a covariance matrix, it has to be positive definite if it's a normal distribution. So in order to do that, we learn the Cholesky decomposition of the covariance. So if you're familiar with Cholesky, it's basically the square root for matrices. So if we learn that and then do a dot product of that with itself, then we get definitely a positive definite matrix. So that's the only slight complexity that we have to deal with. But that's fine. And so if we, so we instantiate our logistic regression, and this is our term to basically take our flattened vector of covariance parameters and turn it into a matrix that's lower triangular. And then multivariate normal takes a scale, a Cholesky scale covariance, so we don't have to worry about multiplying them together. And we do the optimization over that again. And we get the same sort of outputs. Okay, so this one's a little bit more confident, I think just because it's a slightly easier problem actually. And so if we do the same again, we can use our MVM, which is now our posterior distribution. We can sample from that, and that will give us a range of separating hyperplanes. So as you can see, it's not terrible, but because of the nature of the approximation we've used, it's not perfect. So we have mass where there wouldn't be mass in the true posterior, because the logistic sigma, the posterior for the logistic regression is a lot more skewed than the normal distribution. If we wanted to be more accurate, I mean, I've done this for simplicity, but it's actually very, very straightforward. If we wanted to make the posterior approximated by a mixture of 2 or 3 Gaussians mixed together, with the mixture coefficients as learnable parameters, and that would be a lot more straightforward and would approximate posterior a lot better as well. And the good thing is that that's actually incredibly easy to do. All I have to do is slightly change my code here, which implements a multivariable normal into one that implements a mixture of multivariable normals, and then the rest will just work the same. So that's a real positive of this method, is that I can just chop and change my approximation as I want, whereas in the previous one with the Laplace approximation, if I was looking to now do this, the same thing, it would be a nightmare trying to find some approximation from a Taylor series or something like that. Okay, so the next step we can take is we've seen Laplace approximation using the elbow. But actually, there's nothing special about logistic regression. All it is a linear function of the weights and the inputs. We could easily make that a nonlinear function. It's no big deal. There's nothing we've done here which relied on linearity in the elbow. So we can use the elbow as a general loss function as for neural networks. So for regression, normally our loss function, or our log likelihood, would be the log likelihood of a normal distribution or something like that. This is quite straightforward. It's the mean squared error formulation that we will probably use for doing regression with neural networks anyway. And for classification, it's the binary cross entropy. So both of these are quite straightforward. The only difference being that, whereas previously this would be x.w, now it's some function of x and w, which is a neural network, basically. But it doesn't have to be neural network. It could be anything. It could be basis functions, whatever. It all works the same. And we can just again, for this example, I'm just going to use a normal to do the approximation. It makes things easy to work with and to find our way around. It doesn't have to be normal. The same way we could have done a mixture of normals or anything we wanted. We can do that here as well. So the Bayesian neural network looks almost exactly like logistic regression, except this is now just some arbitrary function instead of x.w. And so the code looks pretty much the same as well, actually. We have a little bit more, because we have a lot more weights, there's a little bit more work to do. When we sample from a posterior, we have to chop them up into the right size and things like that, so it's all the matrix products work pretty. So there's a little bit more work, but that's not particularly complicated. So Here I've just got, if we look at the forward function here, I've got 2 layers with a tan in the middle, a hyperbolic tangent in the middle. So this is what, just as an aside, this is one of the reasons I like PyTorch. If you wanted to do something like this in TensorFlow, it'd probably be a real headache for you, and there'd be all sorts of weird TensorFlow-specific reshaping functions you'd have to use. This is just like NumPy. I just do a slice and pass a shape I want it to be in. So that's why I use PyTorch now and I abandon TensorFlow. So here basically is this is the code that implements our neural network. All this other stuff was just pre-processing and shaping. So it's like you all would have seen before, linear combination of inputs and weights, plus do some nonlinearity, and again, and then a sigmoid around the output. The loss function, this is exactly the same as what we saw for the logistic regression case. So binary cross entropy, same, analytical KLD, same, all exactly the same there. And now we can use this to train, for example, this classification problem. It's very similar to the last one. Again, we have the same problems with multivariate nobles, learning positive definite matrices, etc., which we've used Cholesky again. And if we go down, so we can see exactly the same. So our output is basically exactly the same, but now, because we're using a neural network, our decision service can be nonlinear. And we can do all the same stuff that we wanted to do with the logistic regression, we can do it here. So we can see that actually, once we start using the elbow to do things, it's actually everything just kind of falls into place quite naturally. Whether it's logistic regression, Bayesian neural networks, whatever, we don't have to care. Regression, classification, it all just works exactly the same. It's just about identifying the correct probabilistic terms that we use in the elbow. So everything we've seen so far is what we call approximation of a fixed model. So this is, I have some model that I specify and I want to approximate it. But we can take this one further and we can say, what if I want to learn the model as well? So I'm not saying there's a normal prior now with a normal likelihood with a sigmoid around it. I'm saying, well, I want to learn that likelihood. And we can do that as well. So there's like absolutely no reason why we can't do that at all. So this is the fixed model case. Essentially, this is our model here. So this would have been our normal likelihood. This would have been our prior, and this is our approximation. So previously, we were just learning phi, which were our parameters of our approximation. But actually, there's no reason why we can't parameterize this guy as well and do a maximization over both, which is basically what we can do next. So this is the loss function, or the elbow form that we would use to learn both. It's quite simple to do in PyTorch. All we have to do is define a few extra parameters, and optimization just takes care of the rest. So if we want to, now we're going to look at what are called variational autoencoders. So these operate in a very similar way to autoencoders, similar conceptually. The idea is that we use reconstructions of data points in order to learn a model of that data points. So we use a normal, so first of all, we add an additional conditionality. So we have a latent variable, z, which we can think of like a representation. So this is like projecting our data down onto a small condensed representation, which is normally just a vector. It doesn't really mean anything often, like visually, it's just a load of numbers, but it encodes information in a particular way so our network can do inference. So previously all the approximations we did weren't conditional, they were just approximations of the model. But here we can condition on the data points to make it more like an autoencoder. Because for a normal autoencoder, we put a point in, we compress it, then we decompress it, and we compare the outputs. So we can do the same thing here. So we have two distributions. These are basically the encoder and decoder part. So this is the encoder. So given a y, so I take an input point, I encode it, I get a z, and then I put that z into my decoder. So given a z, what's the probability of a y? And so that's like my decoder there. And then I can do exactly the same idea and compare the two, so what I put in and what I got back out, and see how similar they are. And because I'm learning the parameters of both of these, that will work quite nicely. And so what we use is a normal distribution as the output, but the parameters are given by a neural network. So in theory, each data point can have its own distribution. So because the neural network will give different output for each data point, and those outputs are the mean and variance of the distribution. So even though they're normal, the fact that we use the neural network to parameterize it gives some more flexibility, and our final marginal distribution is not normal.
What is the reason for choosing normals?
I think they chose it just for the simplicity of the analytical KLD. Again, most of if you work with VAEs, the normal distribution isn't actually that constraining often. It's more about the flexibility of the elbow and a lot more kind of statistical things you have to look into, because the instruction of the neural networks to give you the parameters gives you a lot of flexibility that you wouldn't kind of see if you just use a normal system. Okay. So basically when we're training this whole system, the weights of these neural networks, F and G as I've called them, are considered the parameters. So these you could have millions of them if you wanted to use a big neural network. So again, just to recap the Y autoencoder, basically because I take a data point X, sorry, I've switched my notation here, which is really bad of me. You take a data point, it goes in, it gets encoded, then goes into our P distribution, which are our decoder, and comes out again as an X point. And then the log likelihood term that we get in the elbow is our reconstruction loss, for want of a better word. So this is just to visualize what happens. I'll give you a minute just to digest that. Okay, so basically we can start here. We have a data point X. We encode it into our first distribution. So this is a neural network. Outputs are a mean and variance, which we then use to sample from. So we sample a Z. This is an encoding of the data. We then pass that through our decoder network, which gives us a Bernoulli parameter, which we then sample from, and that gives us our data point back again. The Bernoulli parameter is if we have discrete outputs, so if we're doing images or something like that, because if it's grayscale, it'll be basically 0 or 1. So this will be a Bernoulli distribution rather than normal. If we were doing continuous, it would be normal. And then we can do the cross entropy between these two. So this is our target, and this is what we predicted. And this flows into the elbow in the same way as before. And then we have the analytical KL divergence between our prior, which is normally standard, and the distribution here. And so this is our loss function here that we take the gradient with respect to and minimize. And then we'll learn the parameters of both this network and this network. So we've got a simple instructive example. So often you'll see in literature people do run these things on faces or things like that. While it's good to see pretty pictures, it's difficult to conceptualize about because we can't really inspect 150-dimensional latent representation. We can't just say, oh, well, that makes sense to me because it's just a load of numbers, right? So a good example that I found was actually using a variational autoencoder to learn a distribution over essentially one-hot encodings. So this is simple enough that we can actually visualize what happens in the network. So this is our input data here. So there's quite a lot of points. It doesn't really matter because they're all the same, basically. And they have ones in one position of 4 dimensions. So the VAE implementation essentially has an encoder network, works basically the same as what you would expect from a normal autoencoder, sorry, except it outputs a mean and a variance instead of just a single output. And the decoder is like a Bernoulli here, so it takes a Z and returns 0 ones. There's a small technical point about, because we use sampling in this process, there's a small technical point about sampling with respect to a differentiable system. So basically, because if I just went to NumPy and sampled, the gradient I got for like the mean of that distribution would be wrong, because the sampling operation is also dependent on the mean. Like if I have a normal that's mean is 0, and then I sample from it, and then I move the mean to like 150, obviously my samples move too. So we have to account for the double dependency on the parameters of the distribution here. So we have to use something called the reparameterization trick. If you're interested, you can go away and read about it here. I've got a little spiel about it here. But basically, we can sample from, for example, any normal distribution by first sampling from a standard one and doing this reparameterization. So the mean plus the standard deviation of what we're looking to sample from times our normal samples. And that gives us samples which are the right distribution, but also then we can differentiate this term by mu and sigma, and everything will work properly. Okay, so, and again, our loss function is basically the same. So we've got our binary cross entropy here and a KL divergence term. And we do, because we're doing mini batch basically, we have to normalize by the size of the patches. Otherwise, we like oversample a KL divergence versus our likelihood. So make our model too simple. And then we have a small function which basically, so the encoder network returns mu and a sigma. And then we have a small function that basically uses the reparameterization trick to generate samples from that. So that's up here, which is the formula I wrote just up there. So basically sample from a standard normal and then times by the standard deviation and add the mean. And so when we can basically just train this now. It's quite straightforward. So we have all the terms here, just reconstruction, and then our loss between our reconstruction and our data. And if we run that for a while, we actually get, and then we plot the z's that we generate, then we actually get a nice distribution. So we can see that the latent encodings that it's learned are separated. So this is, each color represents like one class, for want of a better word, so one position where the 1 is. And so it's able to learn, and so the distribution can separate the different classes. So we actually see that our encodings mean something here, and they actually add information to our system as well. And so this is the same as if we wanted to now generate human faces. The distributions are a bit more complicated, perhaps use bigger neural networks, but actually still the same. And the latent variables that we have would work in a very similar way. So they would encode information about the face that we've just encoded. So obviously we can visualize it because they're normally very high dimensional, but you can sort of kind of see how this thing works. But the good thing is, because it's probabilistic, we get like the learned distribution of the data kind of for free. So we've learned that as part of our neural network, which is nice. Okay, so does anyone have any questions just like at this point?
Sorry,
go on.
Just about that previous.
Yep, cool.
Could you explain what the different dimensions are? Are they weights and subject?
Of this graph here?
Yeah.
Yeah, so our latent representation is two-dimensional. So inside the encoder, yes.
These are weights inside.
So they're not weights, they're actually like the values of the encoded representation, if that makes sense. So, so for example, like for this class, say this was the one where 1 is at the start, its representation would be two-dimensional, and it might be like 1, 1, for example, and that would tell us, okay, this is the encoding of this class, if that makes sense. Okay? Any other questions before we move on? No? Cool. Oh, go on, yeah. Sorry, I can't really see you because of the lights, but go, yeah, go on.
That makes complete sense. So the one question I have is, suppose you don't do this in the variational inference way, you remove the variational part of the algorithm.
Yep.
You would still be left with a latent variable space, I suppose.
Yes.
It would also still be logical.
Mm-hmm.
You see clusters.
Yep.
So in that situation, what would be the main benefit of still taking the variational approach? Because one can also just sample a latent space to get different items on space, right?
Yeah, so I guess the point is that you learn a probability model as well. So whereas with a variational, with just a general autoencoder, there's kind of no probabilistic interpretation. I can learn something, but then if I actually want a joint distribution over faces, for example, I have no way to evaluate it. So like if I was like, for example, let's say I trained it on faces, and then I wanted to take that trained network and say, okay, now this out-of-sample face, I want to classify what's the likelihood that this is a face, for example. I can pass it to the network, and because I have a probability system, it'll probably tell me, okay, yes, it's a really high probability that this is a face, or really low probability that this is a face. So you kind of get like the whole system for free, whereas with an autoencoder, you just get the encoding. It doesn't really give you anything else apart from that, if that makes sense?
Makes sense.
Okay, cool. Right, we all good? Great. Okay, so the next thing we can look at, it's going to seem like a bit of a step away from what we've done before, but it is relevant, I promise. Generally, I think we've probably all seen discriminators before, so essentially just classifiers which classify is it class X or Y. It doesn't try to learn the generative distribution. So these actually have a probabilistic interpretation. It's kind of, if you've ever studied like Bayesian decision theory, you've probably done this and then like completely forgotten about it, and this is going to kind of be like a reawakening for you, I guess. So this is what the output of a normal discriminator would be. So the probability that a data point is class 1, for example. And so we can use Bayes' theorem to do the inversion of this, basically. And if we make the very mild assumption that our data is evenly distributed between two classes, we can essentially cancel the priors, and so we get this term down here. And then if we do a little bit of rearranging, we can see that actually I can write this as a sigmoid, basically, with some log ratio in the sigmoid. So, and this is actually the form we see in a neural network. So if we were training a neural network, this here would be the function, right? So we'd have a sigmoid around some function of our inputs. It'd be a complicated one, but it'd be some function. And so we can kind of see that actually there's like an equivalence here in that if I train a discriminator which claims not to learn distributions, actually it kind of does, because as long as this term here is good, then this logic holds. Obviously, if we don't train a discriminator, it just doesn't work, then we can't apply this logic. But assuming we learn a good discriminator, we can make this equivalence and say, actually, oh, look, there's a relation here between these terms. So I actually kind of get, by training a discriminator on data points, so say I'm training to discriminate between handbags and shoes, images of handbags and shoes. On the surface, that seems like it's not particularly probabilistic, but actually it kind of is, because we can see under the hood we're actually learning ratios of probability distributions here. And these are distributions which we can't articulate. Like I have no idea what the distribution of data points that are, or images that are shoes looks like. It's obviously going to be very complicated. But obviously, from this equivalence, we can see that we learn it. And just to demonstrate this, I've got a small demonstration in here. So again, we're going to use the standard famous normal distribution just because it's a lot easier and it's implemented in PyTorch for us. And so here I've got a really bog standard classification discriminator, just a ton of layers, some values in between, and a cross entropy and a sigmoid on the output. This is like nothing fancy at all, just a discriminator. And so we're going to do, again, some lower dimensional simple data points, just because, again, it's easy to visualize. And so we've got two classes, as I call them. We've got a normal distribution here in the center in red, and then on top of this, we've got a uniform distribution. So the task we're going to initially solve is, can we discriminate between the red data points and the blue data points? Which is what we train our discriminator to do. So we use Adam and just... I've got a little plotting function here, so you can see the progress as it evolves. And this is just the training. So inputs go in, discriminator, gradient, optimization step, and plot every so often. And so we can see that we start off with a really bad decision surface, obviously. It's pretty much random. I hope you can see the data points are kind of like superimposed with a light alpha, just so we can see what happens underneath. And we can see quite quickly it starts to learn a good decision surface. Cool, so this makes sense. I'd say we've trained a good classifier here. It's pretty confident that all these data points here are from, from class 1, and that everything else is not from class 1, so from class 0, whatever you want to call it. But if we use that logic that we found it, before, so if I just get that slide back up. So we can see that there's the equivalence here between this term here and this term here. So if we do a little bit of algebra, we can multiply that out, and it becomes that this ratio here is equal to the ratio of py equals 1 given x divided by py equals 0 given x. So if all I've done here is essentially implement that. So I've been a bit lazy. This here is the probability of a uniform distribution over an 11 by 11 grid. So we've taken, so this is essentially that formula rearranged to make, to change the subject. And if we plot that, then we see, okay, we get a distribution, which is kind of circular like a normal. And if we compare this now versus the true, we can see that actually our approximation is not half bad. As in the peak of our distribution is about right, and the shape looks fairly good. If I zoom out, maybe we can put them. There we are. So even though this method has said, oh, it's discriminative, it doesn't learn a generative model, actually we can see it does, because it's relatively straightforward to back out an approximate probability distribution from a discriminator. And so this is kind of actually important because methods like GANs, for example, use discriminators at their core, and they're like trying to use that as an adversarial mechanism to train their network. But actually we can see that discriminators are learning probability distributions. So that's a really important link to make, because it allows us to take this thing that seems empirical and to push it into probability space, because we can now say, oh, so it actually is learning a ratio of those probability distributions. We'll proceed from there. I haven't done it here. There's a good paper called Adversarial Variational Bayes, which basically takes a variational autoencoder and plugs in a discriminator using exactly the same logic. It's quite straightforward. I recommend that you look into it. And so we can see that. And there's also a series of talks by a guy called, a blog post, sorry, by a guy called Frank, who he has a big series on this kind of using discriminators for implicit generative models as well. But due to time, I've had to skip that out. Okay, so that's kind of the roundup of the variational inference section. Hopefully we can see where this is all going now. We've covered discriminators. We're going to go on to GANs now, and we're going to put it all together. Does anyone have any questions just before we... No? Cool. Yeah, so just to take a step back and say what GANs are. They use an adversarial approach. So I think when they first introduced, they kind of made the analogy of you've got a counterfeiter and the police, and the fact that the police are looking for the counterfeiter makes the counterfeiter make better money, because if he makes bad money, the police find him very quickly, and that by iterating over that process for a long time, you kind of get like a Nash equilibrium of where the counterfeiter is so good the police can't tell, and because they're kind of even level, the police are no longer able to learn from the counterfeiter how to beat the counterfeiter, if that makes sense. So again, this is what I was talking about how we can be heuristically motivated for things, and seeing things through like a variational lens, for want of a better word, allows us to actually introspect into these methods a bit more, because that story is really cool, but it doesn't really let us like apply math to the problem, does it? So it's kind of a useful tool in that sense. So to be formal, the loss function for a GAN is basically, this is the loss function, which is the cross entropy basically, and minimize G and maximize D. So you want the generator essentially to make the discriminator think all its fake samples are real, and you want the discriminator to be able to tell between fake and real samples. So the idea of this is basically, I'd have a load of data, so faces is a common one. I'd put faces in, and I'd make my generator generate fake faces, and I'd put them through a discriminator, and the discriminator would have to tell, is this a real face, or was this one the generator made? And so by iterating through that cycle, you hope that the generator gets so good it can fool the discriminator now, and then you kind of learn a really cool distribution over of how to generate faces. Okay, so we've got, again, a really simple example. Again, low dimensional, because we can think about low dimensions easily. And so this is what I was talking about here in my previous section. So we have two neural networks here, a generator and a discriminator. So this guy essentially returns data in the same format as our input samples, and the discriminator is a standard discriminator like we saw before, returns probability is class 1 or class 0. And so if we imagine we've got this kind of weird correlated plot of points, so this is what we're trying to learn. So we're saying, I want to learn a generator that can sample from this distribution for me. And so all we have to do is train our generator-discriminator pair to do that. So because the original formulation relies on optimal discriminators, so the better the discriminator is, the more signal the generator has to learn how to make itself better, because it can learn what the discriminator was looking for in its samples to basically discriminate between the two. So having a strong discriminator generally aids training. So as you can see, so what I've done here is for every step we take, we change the discriminator 5 times, and we change the generator once. So that the discriminator kind of gets a bit more time to get good at its task, and then that provides much more signal to the generator. Kind of can help stability, but this is a whole massive topic that we have time to go into. So it's quite straightforward. So essentially, the generator takes random noise as a way to make sure that it doesn't just collapse, because if I put a deterministic input into a neural network, I get a deterministic output. And so, of course, you could just like fool that whole system then by saying, well, just remember this one point, and that's the fake point, right? So if you put in normal noise, it forces the generator to be able to generate a range of samples, which is also what we want, because we're not looking to generate me one single sample from this data point, want to sample from it. So this Z here is our random noise, basically. So we generate fake data, and then we run that through our discriminator, and we take the loss with respect to that, basically, binary cross entropy. And the same for the discriminator up here. So this is generator, this is discriminator. They both use the same loss function, but the gradients respect to different parameters. That's the only thing. And when we do that, we see, okay, cool, right, it's all trained. And now we generate some more random noise. We pass that through our generator now. So this is, in theory, fully trained. So by doing this, we're sampling from what the generator's learned. And we can see, actually, the red points are the generator, and the blue points are the inputs. So actually, this looks pretty good. It looks like it's going to sample from there, and we can see, like, if we just do a little Seaborn plot, we can see that these actually look reasonably good. So this is the real data here. So I'm pointing at my screen, and you can't see me do that. This is the real data here, and this is the generated data here. And I'd say, actually, they look right there from very similar distributions. Their margins look very similar. In fact, this one looks more like the original than the other one did. So I would say that's probably a success. And so, again, this process is simple to show with data points like this, but it's no different if we want to generate images of faces. Images of faces are just vectors of data, right? So it's the same principle, just a bit higher dimensional, a bit more finicky to train, bigger neural networks. But the idea is exactly the same. Okay, but so I'm going to talk a little bit around a very common issue that we see with GANs. If you read about GANs for even like 5 minutes, someone will talk about mode dropping. In the sort of basic overview, basically imagine I'm training to generate items of clothing. Mode dropping would be when the system just learns to generate shoes for me. So it may generate amazing shoes, but it doesn't really learn. That wasn't really what I was looking for. I wanted it to generate the whole range of clothes. I wanted shirts, t-shirts, etc. And in theory, this shouldn't happen. So if we use the previous kind of logic that we applied, and we substitute the discriminator for the probabilistic alternative that we showed was equivalent earlier using Bayes' theorem, we can see that we get this term, which is a KL divergence, basically, kind of very related to the general standard divergence as well. And this is symmetric, so it doesn't really matter if I permuted PD and PG. So PD is our discriminator, and PG is our generator. Sorry, PD. I've mislabeled this. This should be real. So this is our real data, and this is our generator data. So if we permute these, it's symmetric. So we shouldn't have like, you know how we saw at the beginning where some formulation of our loss function was mode seeking and some formulation was mode covering. If it's symmetric, you can't really exhibit that because you could swap the problem and it should work the same. So in theory, this shouldn't happen, and we shouldn't have mode dropping in GANs, but we do, and we see it empirically. So, I mean, the short answer is that this logic only holds for being able to do substitution, only holds for an optimal discriminator. So that's probably not true, right? Especially if we're like training on images of faces or something very complicated. I mean, it's a hard task in itself to do discriminative classification 100% on a real general data set. So the idea that we can do it by training like one step at a time and that's always going to be optimal is probably strong. So that we can kind of see where that comes from there. Okay, so this is basically what I just said. In practice, these assumptions that the GAN formulation relies on are not even close to being true. Sometimes the discriminator can be absolutely terrible for half of our iterations. And so we have to look at a different way. So it's possible to derive a result that doesn't rely on the optimal discriminator. This is a paper, like I said, going into ICLR tomorrow, being presented tomorrow. So we're beating them by 1 day. So I recommend you check that out as well. I've got a little demonstration here. Okay, so this is known to be a problem for a little while. So there's a very good, easy to comprehend, basically demonstration of this, which it's going to be the end of the practical session of it. And this is from a paper called Unruled Generative Adversarial Networks. They propose a solution. Whether or not it's a good solution, I'll leave as an exercise to the reader. But basically, the technique they use to demonstrate mode dropping is quite a good one, I thought. So I've reproduced that here. So this is exactly the same code as before. We've got a generator, a discriminator. And now, instead of a single cluster of data points we want to sample from, we're going to pick a diamond. So this is, while this looks a bit nasty, I mean, this is probably literally nothing compared to the manifold that human faces rest on, or horses, or things like that. So these are obviously incredibly complicated distributions, so you should have no problem learning this, right? So this is just like essentially 6 or 7 or 8 normal distributions put in a little diamond shape. And if we train on that, we've got, again, little output to see how it evolves. So as we can see, it starts off in the middle, because this is basically our random noise here, so it's just generating random noise before we train it. And as we train it quite quickly, we see it just zones in on one of the little clusters and stays there, and never really makes any attempts to do any better. I mean, I'm not sure what this is. Maybe it's some attempt to leap across to another one, but it soon decides, no, I'm going to not bother with that. And we basically end up with focusing on one cluster. So the final form, we can see if we generate some samples again and plot those, we see basically all we can do is sample from this one. So we probably learn this one quite well, but if we care about learning a model which learns all of these, I mean, it's probably not quite a success. As we can see from the plots look quite different here, right? So just a small roundup of putting it all together. If you want to, I mean, using the kind of the ideas that I've introduced here, so like discriminators as probabilistic methods and things like that, you can actually reformulate the GAN objective in a more probabilistic sense, and you can get a kind of a unification between GANs and VAs. It's not particularly hard. The paper, they could have maybe done a little bit nicer job making it accessible. The notation's quite dense, and you have lots of discriminators versus other types of discriminators. But I recommend that you go through it. It takes a bit of time, but it's genuinely worth it. And I'm just going to do not very much maths, point to their main result that we can see. So this is the formation they use. A discriminator is a probability distribution, so it's a probability that Y is some class given our data. So they rephrase it like that, and they lump all the data together. So the data that our generator generates and the real data, put it into one data set, and basically use this notation. So conditional on Y, which is the class variable, real or fake. And if you do that, essentially I've skipped out a lot of steps, but you can kind of show that this is the expectation over some joint distribution of our data and our labels over the discriminator. So this is the discriminator here. Again, we won't derive here, but actually, if you now take a derivative of this with respect to the parameters of our generator, you actually get something that's basically this term, less like a half constant, basically, which is a chaos divergence between our generator, the distribution of our generator, and so this term is like our inverted discriminator. So you can see this as being the term, a bit like we did in the discriminator notebook. This is the distribution implied by a discriminator. So this is kind of our learned approximation. And so in VAEs, we had that explicitly. In GANs here, we've managed to back it out analytically using Bayes' theorem, basically. And the Jensen-Shannon divergence is a symmetric distribution. So we can kind of ignore this term because it doesn't, when we're looking at things like mode dropping, it doesn't have any impact. It's just kind of a constant scaling factor, for want of a better word. Like, it doesn't favor one type of mode dropping versus mode covering, etc. So if we just see there, like, so if we ignore the JSD term, we have that for GANs, we're kind of pseudo-optimizing a chaos divergence of P given Q. Now, because we learn both an approximation, which is Q, and a generator, which is P, we kind of have like, we have both situations that we saw before, as in one of them is going to be mode covering and one of them is going to be mode seeking, because depending which one we're taking a gradient with respect to, one's going to be on the denominator and one's going to be on the numerator. So if we look at the generator P, which is the learned model, for want of a better word, we can see that GANs optimize P given Q. So this causes mode seeking behavior. So like we saw in the first notebook where we had that normal distribution focusing on one of the two, this is exactly the same. So our generator is kind of encouraged to focus on a single mode of the data points. So this is where mode dropping comes from, because essentially our generator is mode seeking. So it doesn't matter how good our approximation is, if the thing we're approximating is mode seeking, our approximation is going to be mode seeking. Whereas VAEs, if we remember from the elbow, is the other way around, because we wanted to minimize the chaos divergence between our approximation and the true posterior. So this is why we have mass covering behavior there. So our real distribution, or our learned true distribution, has mode covering behavior. So this is kind of explains some of the things we see with VAEs, because when we see VAEs in literature, they never really compete with GANs. Like if you see human faces from the two, GANs always tend to outperform. And so this is because, just like we had in the first notebook, where we had that normal distribution that covered all the mass, but it kind of didn't really get right the relative proportions of how high these distributions went. So we see this going on again with VAEs, in that we kind of get a better space to sample from, but we kind of don't really ever focus in on one part of that space well. So our samples can be a bit washed out in comparison to something like GANs. But we get the other logic, so we don't get so much mode seeking. Okay, that was kind of pretty much my whistle-stop tour. I guess just in summary, like I hope you followed most of that. And we can kind of see how it's like there's a nice clean path to go right the way from like Bayesian linear regression and conjugate models. We can take that, and by making further and further relaxations and approximating things, we can go all the way through to non-conjugate models, variational encoders, and then GANs, and end up kind of like really at the state of the art of what's going on in deep generative models at the moment. And also, there's always been like a bit of rivalry, like should our VAEs or GANs the one? Which one's the best deep generative model that we should be using? Actually, we're kind of starting to see coming out in the literature now, they're kind of not necessarily particularly different. They started off from very different motivations, but actually we're starting to unify them quite well, and it's starting to become ever more merged, and we see lots of papers coming out now for like that have GAN VAE hybrids and use methods from both. And actually, just as a point for people's understanding and learning, if you want to learn about this stuff, there's tons of people who put blog posts up about like, I generate this picture of a horse. It's really great to see like fake pictures of horses, but if you actually want to like, if you actually want to learn about how this stuff works, you need stuff that you can sort of zone in on. And so there's no reason why these don't work for really simple toy problems. And actually, that's where you should start, not just straight to the big time. That's it. Any final questions from anyone?
Yeah. Ask about the applications. Like it's
oh, yeah.
I ask about the applications.
Yep.
It's obviously very useful to know the confidence of my regression prediction
Mm-hmm.
at some point. But some of us are not as fortunate to work in fashion generating.
Yeah.
Like, what is the application of VAEs or GANs that you've done yourself?
Okay. Well, I mean, so it depends on what we're talking about. So if we're talking about like Bayesian methods, so for getting good tailored predictive probability distributions, like in general, that they are, for me, they have application where you have kind of an asymmetry. So if I'm doing something like NLP, it kind of doesn't really matter. There's no obvious worst case if I misclassify a text point, right? But like I gave the example earlier, if I'm like landing an airplane, it's probably better that I only ever try to land airplanes on things I'm 100% confident are airfields. So you kind of have the asymmetry there. Like there's very little cost for basically not taking an action. So if I'm not confident about something, not doing it costs me basically nothing. But actually doing the wrong thing is really important. So in general probabilistic methods like that, in any sort of frame of work, so like for example finance would be another one, like it's better to not trade than it is to trade wrongly. And so if you're in any kind of environment where I have this biggest asymmetry, it's probably useful to have kind of these good predictive distributions. For VAEs and GANs specifically, I think the industrial uses are kind of only just coming out. I mean, there's obvious benefits to having well-tailored generators that I can sample from. So one that I think actually holds some sort of level of promise is things like weather, for example. Like the sort of systems that go in meteorological systems are very, very complicated. And actually, if we could train models, rather than having to work with a complete distribution that we specify, if we could just train to essentially simulate from this, then that would probably be more useful, because that's actually what we do anyway. We simulate, right? We never like solve the weather function. So I think industrial applications are kind of low at the moment. I think people like Twitter as well use VAEs and similar kind of methods to do things like image compression. I think it's very much R&D stage now, but this stuff is like definitely on the up, and everything starts out off with like simple toy examples, and very quickly we kind of ramp up. So for me, it's like a continuation of the stuff that we've been doing before, but a lot more complicated. Okay. Yeah, go on.
So, cool talk, by the way.
Thank you.
I noticed you're using PyTorch.
Yes.
It's one of the choices in deep learning.
Mm-hmm.
TensorFlow might be another one.
Mm-hmm.
Is there any reason in particular why one might favor PyTorch for these sorts of things? And if possible, TensorFlow just released some of that probability stuff.
Yep.
Had a look at it? Does it compare?
Yeah, so I guess you're talking about well, so TensorFlow has Edward, which is a probabilistic programming language, and they've also like integrated some of that into the core, because I think they employed Dustin Tran for a bit. For me, like, I think it depends what you're doing, because you can sort of kind of see TensorFlow as like a compiled language. So, as in, you kind of specify everything up front, and as soon as anything doesn't work, it just like blows up on you, basically. So, maybe if you're doing something like your Twitter and you're running something in production, you maybe want that certainty of a kind of compiled framework. So, I know that like we just have a nice explosion when things don't work out, whereas PyTorch I see is much more like an R&D framework. So if you're looking to mess around, you don't have to worry about, oh, have I just wiped my computational graph, or like, what's happened? Have I just like, because I've run 2 cells in a notebook in the wrong order, I've like attached it to some weird point on the graph, and now everything's exploded, and I don't know why. So like for me, my kind of process is generally like, I'll mess around in NumPy for a bit, and then I'll go, cool, this looks like something I want to take forward. And you'll kind of go, all right, well, PyTorch is basically import PyTorch, works up NumPy 98% of the time. So I don't think there's any particular pros or cons. I think it just depends on what you're doing. If it's an R&D stuff, I favor PyTorch, but I know people who use TensorFlow for R&D. It's pretty much personal preference, I think. Okay. Any other final questions? No? Okay, just to finish off, I won't spend any time on it. There's a few references, further readings, good blog posts on some of these topics. It's like literally a spider's web. If you try and start digging into any one of these, you'll say goodbye to your weekend probably. But these are really, really good places to get some introductions and jumping off points for more stuff, basically. And the paper that I referenced right at the end was this one here on unifying deep generative models, ICR 2018. And then my blog, which has a few of this stuff here that I do when I'm bored. So, okay, that's all. Thank you.